Hello, my name is Isaac Saruk, and today I'm going to be presenting my Masterworks, Beyond Vision, Understanding Space Through Physics. Has anyone here seen this movie? The movie Interstellar came out in 2014. One thing that made this movie special was that it contained a computer-generated video of a black hole, which ended up looking something like this. It was made purely from mathematical formulas developed by scientists. You see, what makes a black hole so interesting as compared to other astronomical objects is the fact that its existence was predicted rather than discovered. In fact, we've only ever taken 2 photos of a black hole, the first of which was taken in 2017, 3 years after the movie Interstellar. These photos represent one of the most impressive scientific achievements ever accomplished and are a testament to how far we've come. But before we get into that, I'd like to talk a little bit about me. When I was young, I loved a book called A Child's Introduction to the Night Sky, specifically a chapter called What We Cannot See. This chapter covered gravity, dark matter, black holes, and neutron stars. At the time, I didn't understand a word I read about then. Despite that, the idea of something so powerful, so massive, yet so unknown fascinated me. I would spend my free time researching whatever physics phenomenon had caught my interest that day. What never failed to blow my mind was not the what, but the how. How were we, being so minuscule and insignificant compared to these things, able to know the properties and rules that defined objects unimaginable in both scale and distance from us? In 1675, Sir Isaac Newton wrote a letter to Robert Hooke, saying, "If I have seen further, it is by standing on the shoulders of giants." The reason that we are able to know the unknown is because of the centuries of mistakes and successes made by the giants before us. In this paper, I will be writing about the history of astronomy with the focus on the invention and evolution of telescopes and the development of a cosmological model. I will also be discussing the processes, outcomes, and factors involved in astronomy and their importance to cosmology as a whole. Now that we have covered that, I'd like to go back and talk a little bit about the beginnings of the development of a cosmological model from the age of antiquity. Before telescopes existed, everything that was known about space was based purely on observations by the naked eye. This means that many things we think of as obvious today were heavily debated at the time. An example of this was the question of why planets moved across the sky. You see, we now know it is due to their orbit around the sun. However, this wasn't the case at the time. Back then, there were 2 groups of thinking on why this was. One group believed that the planets moved across the sky in their orbit around the sun, and the other believed it moved across their sky in the orbit around the Earth. This was heavily debated until 3rd century BCE, when Aristotle, the famed Greek philosopher, concluded that the Earth had to be stationary, as when you threw a ball up into the air, it didn't land behind you, as he figured it would if the Earth were in motion. This is when the idea of a geocentric universe started to become widely debated. It stayed like this until 2nd century CE. This is when Roman astronomer Ptolemy again proposed a geocentric universe. The difference between Ptolemy's model and earlier iterations of a geocentric model are the order in which the planets are described to orbit the Earth. This stayed in place for many centuries, partly because it agreed with how the Catholic Church interpreted the Bible. Even though it was accepted as true, Ptolemy's model had many flaws and was adapted many times over the years. It wasn't until 1,300 years later, in 1584, that the idea of heliocentrism was reintroduced by Nicholas Copernicus. Unfortunately, though, it was not taken very seriously until 1613, when Italian polymath Galileo Galilei published his paper, Letters on Sunspots. Now, this paper was important because it proved that the geocentric model of the universe was untrue by outlining his recent discovery of the phases of Venus. This is because in order for Venus to have phases, it has to be orbiting the sun. This discovery and the consequential overturning of the geocentric model was due to one invention: the telescope. The first telescope was named the Galilean telescope, after its inventor, Galileo Galilei. A Galilean telescope works by having a convex lens on one end and a concave lens on the other. This lens focuses the light into a point and magnifying it. it also flips the image upside down, whereas this lens flips it back up for the viewer. While this did allow for the discovery of the phases of Venus, proving a heliocentric model, it was very limited, as it was only able to provide 30 times zoom. This was because in order to increase zoom, this lens had to be bigger. And the bigger this lens was, the smaller this one was. Obviously, this had a limit. In order to fix this problem, eventually, this lens was changed to a concave lens, changing the design to this. This further increased magnification, but didn't flip the image back right side up. This didn't really matter to astronomers when looking into space. In order to further increase magnification with this new iteration of the telescope, astronomers had two options. They could either decrease the curvature of this lens or increase the curvature of this lens. Sorry, I meant increase the curvature of the one next to the eye. Increasing the curvature didn't work as it made it act like a prism. This blinded the astronomer as the image was covered in rainbows, making it completely ineffective. However, decreasing the curvature of the further lens worked great, other than the fact that it meant that the length of telescopes had to increase, eventually leading to telescopes over 100 feet in length. This one pictured here was 148 feet long. This new age of astronomy brought forth many new discoveries and theories, one of the most important being proposed in 1687. In 1687, English physicist Sir Isaac Newton published his book Philosophiae Naturalis Principia Mathematica. The reason that this book was so important was because it outlined two of the most important theories in classical physics, those being the three laws of motion and universal gravitation. Newton's three laws of motion are as follows. Number one, a body remains at rest or in motion at a constant speed in a straight line unless acted upon by a force. Basically, this means that things won't move unless they are moved, and things won't stop unless they are stopped. Number two, when a body is acted upon by a force, the time rate of change of its momentum equals the force. In simpler terms, this means that heavier things require more energy to move. And lastly, if two bodies exert forces on each other, these forces have the same magnitude but opposite directions. Every action has an equal and opposite reaction. The other important theory in this paper, that being the law of universal gravitation, states that every particle attracts every other particle in the universe with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Basically, this means that every particle in the universe is constantly attracting each other. This is gravity, or at least Newton's understanding of it. These laws together make up what is known as classical physics. While classical physics are used today, they are missing three big pieces and are unable to explain many things. These three big pieces are the theories of general and special relativity and quantum mechanics. To put it simply, special relativity is used to explain the properties of objects moving very fast, like light. General relativity is used to explain the effects of objects with great mass, like black holes, and quantum mechanics are used to explain objects that are very small, like atoms and quarks and neutrons and whatever. That being said, the laws established by Sir Isaac Newton are still used in many select cases. The introduction of this new set of universal laws raised questions from experts because of their implications. For instance, if everything attracted each other, how come the universe didn't just collapse in on itself? Isaac Newton answered this question by saying that the universe was like a grid, with stars spread out evenly across this grid in such a way that they were all attracted to each other equally, holding the universe in place. Funnily enough, this conclusion raised more questions than it answered, and resulted in something known as Obler's paradox. Obler's paradox is basically, if the universe is infinitely filled with stars, how come the sky isn't infinitely bright? The creator of this paradox, Dr. Heinrich Obler, thought that this was because space slowly absorbed light, although he had no proof of this. The first scientifically backed resolution to this problem came surprisingly from American poet Dr. Edgar Allan Poe. He thought that maybe the universe was just too young, so all the light from stars hadn't reached us yet. While also wrong, this solution is much closer to the actual reason our sky isn't flooded with light. That being the fact that the universe is expanding infinitely outwards, preventing that light from reaching us. Now, I'm going to skip ahead a few hundred years to the next big advancement when it comes to observation. That being the invention of radio telescopes. But before I can explain radio telescopes, I need to briefly explain what the electromagnetic spectrum is. As I assume everyone here knows, light primarily acts as a wave. This means, like a wave, it can exist in a range of different frequencies. The light that we can see only exists in a very small range of frequencies. So of this whole spectrum, telescopes that rely on our eyes can only see a tiny bit of all the light in the universe. That means that everything that we are observing was very, very, very limited. That is, until the invention of the radio telescope. The radio telescope allows astronomers to see much more of the universe than they could with the Galilean telescope. Although with the invention of this telescope, a very curious observation was made. When the telescope was pointed into space, it received a uniform signal regardless of the direction into space that it was pointed. The reason that the signal was so important was because it proved the Big Bang theory, which at the time was heavily doubted by physicists. How did it do this? In order to explain that, I first need to explain what this signal is. The signal that astronomers were receiving was what is called the cosmic microwave background, or the CMB. The CMB was created around 380,000 years after the Big Bang during an event called recombination. Why? In order to explain this, we need to go back even further. Around 1 second after the Big Bang, the universe was too hot and dense for anything other than electrons, neutrinos, and quarks to exist. These quarks aggregated eventually and formed the first protons and neutrons. Around 3 minutes later, the expansion of the early universe had cooled it enough to allow hydrogen nuclei and some helium and lithium nuclei to form from the protons and neutrons in a process called Big Bang nucleosynthesis. For the next 380,000 years, the universe stayed like this. Eventually, though, it had cooled enough that the rough electrons were able to form hydrogen, helium, and some lithium. This mass formation of atoms released a lot of protons. This was recombination, this release of protons, or light. Now, as the universe expanded from the Big Bang, what happened to these light waves is they expanded too, as they traveled across the universe. This caused them to undergo an effect called redshifting, which I will get to in just a moment. This turned it from light waves, which we can see, into radio waves, which we can't see, by stretching them. So when we point radio telescopes into space, we are detecting all of these ancient radio waves. If we could see radio waves, the sky would be very bright. Moving on, if you remember just a second ago, I mentioned something called redshifting. Redshifting is when light waves stretched. It's called redshifting because the more stretched out a light wave is, the redder it appears to us. There are three main things that cause redshifting, but before we can understand those, we need to understand a very important concept called the Doppler effect. If something is emitting a wave, be that a sound wave or a light wave, the frequency of this wave will change based on the movement of whatever is emitting it. Here's an example of that. When this car is moving forward, you can see that the sound waves emitted in front of it are scrunched, whereas the sound waves emitted behind it are expanded. An example of this that you can observe is when a cop car is coming towards you with its siren on. The closer it gets to you, the higher pitch the siren will sound, and then the farther away, the lower pitch it'll be. Now I mentioned that there are three types of redshifting. One of these types of redshifting, basically, or called the relativistic redshift, is basically just when light undergoes the Doppler effect, plus some other complicated time stuff. The other two types of redshift are called cosmological redshift and gravitational redshift. Does everyone here remember when I mentioned earlier that the universe is expanding? Well, this expansion causes planets and stars and everything else in the universe to be pulled away from each other. Now, most of these stars and galaxies that you see when you look up into the sky aren't moving away from us because they are in our galaxy, which is held together by gravity. But if scientists use really powerful telescopes and look past our galaxy and instead look into other galaxies, the farther away they look, the redder these galaxies look, like this. This galaxy is the furthest galaxy ever photographed. Do you see how red it is? This is cosmological redshift, when light stretches because of how the universe expands. One really special thing about cosmological redshift is that we can use it to see how far away things are because we know exactly how fast the universe is expanding. Lastly, we have gravitational redshift. One of the laws of physics is that anything that has no mass will always move at 299,792,458 meters squared, or the speed of light. But let's say this light passes by something that has a lot of gravity, like a black hole. As it passes through the black hole's gravity and tries to leave, it gets pulled back. But even though it's being pulled back, it can't slow down. So instead, it loses energy by lowering in frequency and stretching out. This is why photos of black holes are so red. Now, I've barely even scratched the surface when it comes to space and all the ways we learn about it, but I only have so much time. Before I'm done, I have a few final things to say. The study of cosmology as a whole is a testament to the human spirit, representing innovation and dedication. The reason that I chose to do astronomy for my Masterworks was because I've always been fascinated by the unknown and the future of astronomy. I present this project with a new respect for the many lifetimes of work done in order to bring us to our current understanding. How even the most basic, the most fundamental laws are the results of the dedication of those who pioneered this field. In the future, I hope to use the knowledge gained here to further pursue this as a career path. That is one reason I value this opportunity so much. To write and present this Masterworks is because I feel I can help grant me those opportunities in the future, and because it has helped instill the dedication and work ethic needed to effectively pursue those opportunities. However, I couldn't have done this without the help from a few amazing people. First, I would like to thank Adrian Van Lith-Theota, my external advisor. You helped keep me on track throughout this entire presentation, and I know sometimes it may have been hard when I had to rewrite my script a couple weeks before we presented, or fix all my sources in the paper after it was due, but I really couldn't have done this without your help. Next, I would like to thank Graham and Carla Saruk, my parents. Thank you for looking over my paper and reminding me to work on it. Without that, there's no way I could have gotten this done in time. I would also like to thank Sam, Ben, and Maddie, my brothers and sisters, for leaving me alone when I was trying to do my paper. I would like to thank Jen for also keeping me on track. Without you, I wouldn't have gotten anything done in school. Ethan Sun and Guillermo Spears aren't here today, but they both worked as my internal advisors. And Ethan provided so much valuable information that, because reading these articles on the internet, learning about this, I couldn't understand a word they said, but he helped break them down and explain them in a very usable way. And Guillermo Spears helped me see the beauty in the universe rather than just the science behind it. And lastly, I would like to thank my classmates for, going through the same thing that I was, struggling with this. It made it feel a little less hard.
Mr. Saruk, that was an excellent presentation, and as a former science teacher here, I was thinking, the rest of the kids here, I think you got to about 5 minutes in before you might have lost them. But what do you think, 5-10 minutes? The whole thing, love it. Okay, so there should be lots of great questions, and you covered a great base of us being able to understand the physics that go behind this. There's so much more, and we're on the way to learning about that stuff. So we're going to start with Adrian as your faculty advisor for questions.
Mr. Saruk, I don't think you could choose a bigger topic. I won't just do space, I'll also just throw in physics. Nice. And yet you managed to make it accessible and made me understand it and made us understand it. You really took on an enormous challenge for yourself and persevered through it and succeeded tremendously. I am hugely impressed by what you managed to do, and humbled, actually, to see how you managed to pull it together. It's really a remarkable thing. Well done. My questions for you, one is from the beginning of your presentation. You said that the black hole, what it looks like, was predicted long before it was observed. How? How does this work?
Okay, so a lot of what comes from observing space is trying to learn what the basic rules of the universe are. Because when we just study on our planet, that's a very limited sample size, and we get to see very little of what can happen with the building blocks of the reality that we live in. So when we look out into space, we can see all these interactions that couldn't happen here on Earth that give us a clue about how the universe works. And then with these clues, scientists try to build a base, and it's usually like a mathematical base of what different particles there are and how they interact with each other and how that works on a larger scale. What happened with the black hole is Albert Einstein developed his theory of special and general relativity, which talked about how he thought gravity worked, which was different from Newton's. Newton said that it attracted everything, whereas Albert Einstein basically said that anything with mass will bend everything around it, which therefore causes things to fall into it. But with this theory, he was looking at the math and stuff, and he realized that this would mean that anything that has a great enough mass, like a black hole, would collapse into a point of infinite density. And this was something that he thought was impossible, so there's no way that this could have worked. But then we looked into galaxies, and we saw them all they were staying together for some reason and orbiting around a center. And then this started to lead us to, it helped prove his theory of general relativity. And another example of something that was predicted was the cosmic microwave background. The creator of the Big Bang Theory predicted that if you pointed a radio telescope into space, you would detect this radiation everywhere, which it did. So we can predict what we think the universe will look like based on the laws that we've established for it.
Nice. Great answer. Yeah. So my second one is not to do with math, I think. Although maybe Jen can say everything's to do with math. We got a lot going on. I know you said Earth is a small sample size, but it's all most of us know. And there's a lot going on here. We got social issues, we have environmental issues, we got economic issues, we have homework. Lots of stuff and lots of issues that we have to think about and we would consider important. So why bother spending so much time, so much energy, so many brilliant minds like yours thinking about space when we could apply that energy to other issues?
I think that there's really two explanations I can have for that. One of them is that by learning about space, as I mentioned, we learn much more about how the universe works. And with this understanding of the basics of the universe, we can develop new technologies that have never been seen before, and these can be used to advance our own society. But I think the more important one is that sometimes it's okay to learn about something just because it's interesting. And when we learn about space, when we try to understand space, we are able to understand more of what our place in the universe is. Because it's so huge, and we are just such a tiny part of that. And I think it's important for us to realize that, but also realize how special it is that we have this as compared to everything that is out there, and the amount of amazing but incredibly hostile things that exist.
Great answer. Thank you, Ashley.
Do you have questions from the other advisors or no?
I do not.
Okay. Mr. Saruk, I'd like you to actually tell your audience about who your advisors were, and also when you started this project, it looked very different than what you ended up with. So could you go through that process with your audience?
Originally, I wanted to do astrophotography with a telescope and take pictures of space. But the more I did research into that, and the more the project started to develop, I realized what interested me wasn't really the artistic side of it, more the scientific side of it. So my original advisor, Guillermo Spears, he's an astrophotographer from Peru, so his focus was much more into that, and then realized that he didn't really have the knowledge he needed, but he was super helpful and did provide a lot of great information, which I did end up using here. And then after that, we reached out to UBC, and Ethan's son, who's a student at UBC studying theoretical physics, I think. We set up a few Zoom calls with him, and we emailed back and forth, and he was super, super helpful to this operation.
Yeah. We have huge thanks to the people that do volunteer with our kids, because it goes somewhat a bit beyond what we know as faculty advisors, so it's wonderful to have them mentoring our students. Questions from the floor. Mr. Spore, why don't you start?
Incredible presentation, Mr. Saruk. That was very interesting. My question is about Galileo. So the church denied that his theories were correct. How do you think religion has adapted to incorporate physics and, I guess, astronomy?
I think really interestingly, one reason that his theories were rejected because the church at the time had become more of a political power rather than just a base for religion. So when this theory was proposed and it fit with everything that had been observed at the time, it didn't really fit with how the Bible was interpreted. So this was seen by the church as a losing of political power. So, but I think as it has evolved, there have been many new interpretations of a bunch of religious texts, be that the Quran or the Bible, that allow for a lot of these new observations within those religions. Although there are some religions or sections of religions that don't necessarily agree with a bunch of the information that has been taught by scientists, and that has led to a lot of conflict. Well, not physical conflict, but some physical, but lots of mental and verbal conflict.
Mr. Whitty.
Fantastic presentation, Mr. Saruk. I'm so proud of you. I was very sad when I heard that you weren't going to do astrophotography, and now you proved me wrong. This was so much better than I thought it was going to be. I was sad that you weren't doing photography, but I think you did a very, very good job with this. And I was entertained the entire presentation. But I was just wondering, if you were to name a star, what would you name it?
Most stars right now have really, really, really boring names. They're just a bunch of numbers and letters. The original answer I thought it wasn't quite appropriate for this presentation, but I've got no idea.
Nope.
Amazing job, Mr. Saruk. So, what was the most surprising thing you learned over all years?
Well, researching redshifting, I knew a little bit about it, but what I didn't realize is how much it affects everything that we observe. So when scientists look into space, they have to account, because the photo or the image that they're getting is nothing like what it would be like to actually be there. Because first of all, a lot of those photos of galaxies, since they're so far away, that is what those look like billions of years ago, because the light has just traveled to us. But yeah, it's incredible how much math has to go in just to looking at an image to see if you're interpreting that correctly or not.
I just wanted to say that when I'm thinking back at the science curriculum, that you guys learned about the electromagnetic spectrum, I think in grade 6 or 7. Is that right? Grade 6 or grade 7? Do you know about the electromagnetic spectrum? Grade 8. Interesting. And I know that Pam talks about redshift and a little bit about the Doppler effect. You did an excellent job teaching that.
Thank you.
Because physics goes beyond what we can see, it is really difficult to get it to a place where everyone can understand that, but you did an excellent job, so good for you for that. You have a future career there. Mr. Becky, come on up.
excellent presentation, Mr. Saruk.
Thank you.
So you talked about red shifting, but is there such thing as violet shifting? Things are moving towards us quickly?
It's called blue shifting, but yeah, when something is entering, like I talked about how when it leaves a gravitational well, it turns red because it's expending more energy. The opposite happens when it enters that well. It turns more blue as it's losing energy. And yeah, blue shifting is a very real thing that happens all the time. But it's less relevant to us because red shifting can be used to tell how far away things are, like I mentioned. So everything that we look at red shifts, but not everything blue shifts.
And also a secondary question: would the Andromeda galaxy eventually start turning blue as it enters kind of the Milky Way gravity well?
That's really interesting. I don't think it's moving fast enough or far enough away for that effect to happen, because in order for light waves to bend like that at all, they have to be moving very, very, very fast. That's why that photo of a galaxy, it was very red, but that is billions and billions and billions of light years away. So that effect is very, very slow, and the Andromeda galaxy is relatively quite close to us.
Thank you.
Mr. Olson.
Incredible presentation, Mr. Saruk. A lot of pressure being the last one. You did fantastic. So I must ask, in that photo of the black hole, and we can see that it was red shifting, right? What color do you actually think black holes are? Other than the event itself.
Well, the color that you see from a black hole obviously isn't the black hole itself. It is everything around the black hole moving very, very fast because of its gravity. Anything that actually goes near the black hole disappears, and the light is pulled away. So that is perfectly black. But everything around it that's like spit, it's very, very hot. So it's difficult to say what color it actually is, because once those light waves are emitted, they are red shifted. So if you were to go right up to a black hole, that's what you'd see. You'd see the red, because the light can't escape without becoming red.
Right. Then my second question is, what do you think is beyond an event horizon?
Man, okay, so for anyone that doesn't understand, the event horizon is the area around a black hole in which nothing can escape. So when you see just like that black orb in the middle of a black hole, that's not actually the black hole itself. That's just the point in which anything that gets near it cannot escape. So what is inside of it is what's called a singularity, which is it's a point that's infinitely small and infinitely dense. So there's really no way to say what that would look like or what it can do. Some people think it's a wormhole, but nobody knows. Because it kind of breaks physics, having something that's infinitely dense like that.
Excellent answer. Juno.
Well done, Mr. Saruk. It was very easy to understand, and I was awake the whole time. Very good. I have two questions for you. The first question is, okay, let's just say, you're answering Adrian's question, and you said that these like astronomers, they all like predict after clues that come off. While you're doing your research, like you got clues from your research. Did you make any predictions yourself from those things? Like, would you ever like from the clues? Did you ever find it?
I'll be honest, most of the research that I did went right over my head until I had to read it many, many times to understand it a little bit. One really interesting thing that I did read about is something called a graviton, and this is something that, from what I have read, I believe that it exists, though it's debated still. And basically, a graviton would be a particle that is what is gravity. It is the particle that transmits that force. So it's very, very small. It'd be the smallest thing that we've ever found, but.
Very
Yeah,
good.
scientists are trying to
My
find
second
that.
question is, since you're all into this stuff and you're really good at explaining everything, and you've already clearly showed your passion for all this stuff, would you ever think of becoming like a scientist or like an astronomer?
I've definitely thought about becoming an astronomer, but that requires a lot of schooling, and it's not a lot of pay. So it's definitely an option, but I'd have to look at the logistics of it first.
I'm sure you make a lot more money as a gas admission. Come on, Anna.
remember them. My first question is, with everything that you've learned in this project and with your previous knowledge, there's that whole idea around extraterrestrial life. What are your predictions around that? Is it out there somewhere in the universe, or?
It kind of, I think it has to be, based on, we have looked, when looking for extraterrestrial life, what we tend to do is we tend to look into other solar systems and look at the chemical composition of the atmospheres in the planets of the solar system. And then we can predict if what we understand life to be could live in that, like if it has oxygen or whatever. And one reason we have tested, in comparison to everything there is, we have tested nothing. You could say that we have tested none of it, and that would be basically true, because there's just so much. And then also, we're assuming that life on another planet would work similar to the way that life works here, which we have no proof of. So I do believe that somewhere, I have no idea if it'd be advanced or not. I don't believe that there is advanced civilizations out there yet. I think we probably would have detected them somehow because they send off information. But I think there really is no way to know.
Thank you. And my second question is, with how the universe is expanding and with how the stars light, with how long it takes to reach us, there's people saying that within a certain amount of time, all the constellations and things we see in the night sky, when we look up, they'll be gone. It won't be recognizable anymore. What do you think will be the first thing to leave our sight? Which constellation do you think will be the first to go?
I'm not sure about which constellation, but I do know there is a star called Betelgeuse, which is the biggest star that we have seen, and it is estimated to go supernova in 20 to 100 years, and that'll make it appear to be day for a month or so. For us, that's how big that star is. Or at least for a few days, but then it'll look like there's a sun in the sky, even during the night for a month or so.
For the next 20 to 30 years?
20 to 100. Or that's what we think, though we predicted it to be in 100,000 years before, so we really have no idea. But that's what the current prediction is.
It's a pretty cool thing to look forward to.
Yeah.
Scott, go ahead.
Thank you, Mr. Saruk. Really compelling and captivating presentation. I'm so awed by your knowledge here standing before me, and I'm curious if in addition to all that you've learned, like I have heard people say, as much as we can look out into space and to all those distant phenomenon, science is also looking like the other direction into things that are here and matter on Earth, etc. And what they're finding is that it's mostly space too. So I'm just curious if your process of going through Masterworks included anything looking the other direction.
Oh, definitely, because everything everywhere in the universe is built out of the same stuff. So when we're looking at like a star that's really far away, there's only so much that we can learn about it by just staring at it, right? And we can read the information that it's giving off. But another way to explore it is to look at what it's built of, and that is everything that's here. So if we can understand how those work, then we can probably understand how it works. So there's been a lot of work with astronomers. There's what's called a particle collider, and what that does is it shoots things at each other really, really fast, and then they blow up into smaller things, and then we see what those smaller things are made of, and so on. And then that has helped us understand quantum physics more, and quantum physics helps us understand how everything out there works. So yeah, I had to do a lot of research into that.
Thank you.
That's, yeah. Dr. Spears, come on out to the microphone.
I don't actually have a question, I have just some observations. I would say you're an incredibly accomplished speaker.
Thank you.
You do that very well, and you explain things very well. You're a good exemplar, I think, of what Masterworks can be. And so, kind of an observation, you kind of touched on it, and I don't know if it's clear to people, but when Adrian says, "Well, I can barely understand what you're saying," or you know, we have a situation with Masterworks when students work hard. You can be an equal or a better in your knowledge to population adults, and that's a significant accomplishment. And you alluded to in your presentation, I didn't really understand the papers that I was reading, and it took a long time, but you read them and read them and read them, and you got some help from advisors, such that you were able to come to this place today and demonstrate a level of competence. So the observation is anybody can do that. But the thing is, it takes hard work. You gotta reread the papers, you gotta get help, you gotta be passionate about it and dive in. But when you do that, you're 14 years old for crying, right? When you do that, anyone can achieve it. So congratulations.
We have time for a few more questions, so please, Kabir, come on.
So, I too want to be an astrophysicist, but I have a question for you. What is your view on the information paradox? Do you agree with the solitary theory?
Well, about the information paradox, if I'm clear, that's about black holes, right? Isn't our current understanding of them that Hawking's radiation solves that and is able to
No,
explain?
Hawking radiation makes the paradox, but then black holes explain.
Right. Man, that's tricky. So, I think because black holes, everything that we learn about space is done through, basically we read electromagnetic radiation to kind of understand what we're looking at. And then with the black hole, it is a point in space that we have no information about because no electromagnetic radiation can escape it. So I think we know how black holes work in physics, like what causes them and stuff. But recently there have been a lot of new theories about how they work that way. Like string theory considers them just a ball of those strings in string theory, which is completely different, and that would solve the information paradox, I think. But I think we really have no way of knowing. I don't know enough about it to give an answer on what I think the solution is, because no one really does, and there have been a lot of explanations, but I think in their nature, since they don't work with physics very well, I think it's hard to explain.
Do you know about the solitary theory?
No, I can't say I do.
And we have a Masterworks now, 3 years from now. Mr. Lee, come on up.
Fantastic presentation, Mr. Saruk. It was really interesting, and then was really easy to follow through. I have a question. You can say, I don't know if you would like, but like, what do you do? Okay, 2 questions, kind of based on 1 question, but what do you think happens, like, in the point where physics breaks down, like beyond the speed of light, inside a black hole, or like absolute zero? And do you think we will ever know?
Well, with beyond the speed of light, a lot of the work I've seen being done to try to figure out how that works has been trying to work around it through bending space-time to travel at great speeds or whatever. But I think that whenever people try to explain what would happen if you do move faster than the speed of light, they use the laws of physics to explain it, which doesn't really make sense if you think about it, to use laws of physics to explain something that doesn't work with the laws of physics. I think that it's impossible, because if we're right and that is the speed limit, then I think it's impossible to know what would happen, because everything that we know contradicts it happening. But with black holes, I think eventually we could learn how black holes work, because there's something that we learn about, and we learn so much about every single year. So I think our understanding of them is just growing and growing and growing. I think eventually we will figure out what's inside and the answer to the information paradox and stuff like that.
So from what I got, it's like some problems we can solve. But
Some we can solve,
like just unsolvable.
but yeah, some are just unsolvable because they don't work with
Like I'm
the
also
tools.
for my past Masterworks, there's also some problems that are like just
Yeah,
there's
exactly.
an equation that proves that it cannot be proved right, and there's another equation that proves it cannot be proved wrong.
Yeah, exactly.
Thank you very much.
Mr. Sport?
One last question. Did you do any research into the unified field theory?
Not a lot. I kind of, no, most of my research was focused on redshifting and then general and special relativity. I did some work on particle wave duality and then some with gravity and kind of gravitrons and bosons and stuff like that. But no, not as much as I should have.
Julie, come on up.
Wonderful, absolutely beautifully presented, Mr. Saruk. My question, I think, is related to a lot of other people's, but in order for us to know the unknown or to try and distill the unknown, there's a lot of creativity that comes in a lot of that. And you have this artist mind as well as the scientific mind. And I think my question would be, do you ever think that we will come to the point where it's no longer a creative process and it's everyone will see it the same way and it won't be this ambiguous question? Because I see my world changing on the daily. Do you think in my lifetime we will have those answers to those questions?
There have been many times throughout history when people thought they knew how the world works, and every time they have been wrong. And even now, there are theories from 10 years ago that are completely incorrect. And like Einstein's theory of general relativity, which we thought was completely true for the longest time, doesn't work with quantum mechanics. Like those two do not work together. One of them has to not be true. So even theories like that we thought were full watertight just don't work at all. I think it is impossible to know that we know everything. So I think there will always be people challenging it, but right now I think scientists generally agree, or at least the people in that higher level generally agree on how things work. And there are some theories that'll pop up right now, or not right now, theories that'll pop up from other people, but they're usually advanced and tested quite rigorously, and they don't work as well as what we have now. So I think right now we're in a good spot, but we still have so much that we don't know.
I love that you see the beauty in the unknown as well. Thank you, Mr.
Harper, come on.
Amazing job, Mr. Saruk. It was great. I was wondering, for a lot of people like to partake in astronomical, even the sea, because they enjoy the not knowing but trying to understand constantly. Do you say you'd be in the factor that really enjoys the constant finding, or would you say you're maybe the side that's like, I really want to figure this out?
It was interesting because when doing my Masterworks, there were things that at the beginning of my Masterworks I was like, oh, so this is how it works. And then later on, I was completely wrong because new theories are always being developed and everything. And I think that's part of what I love, is that there's always something new coming out, which opens up so many new possibilities for how it works. And I think it would be nice to know, but I don't think we ever can.